Bismillahirrahmanirrahim. Well, introduce myself. My name is Namra Server and I'm Department from BS Chemistry. I will submit it to the presentation of Dr. Hammad Mujid. Today we have discussed about the topic of cement industry. So let's start. What is cement? Cement in general adhesive substance of all kind, but the binding materials used in building and civil engineering construction. Then what is cement industry? The cement industry is one of the main industries necessary for sustainable development. It can be considered the backbone for development. The main pollution source generated from cement industry is the solid waste called cement bypass dust, which is collected from the bottom of the dust filter. Next, I will discuss history of cement industry. Cement, as we know, it was first developed by Joseph Aspden, an enterprising 19th century British stonemason, who heated a mix of ground limestone and clay in his kitchen stove, then pulverized the concoction into fine powder. The result was the world's first hydraulic cement, one that hardens when water is added. Next, composition of cement industry. Cement is manufactured through a closely controlled chemical combination of calcium, silicon, aluminium, and the last one is iron and other ingredients. Next, I will discuss classification of cement industry in front of you. Cements used in construction are usually inorganic after lime or calcium silicate based, which can be characterized as non-hydraulic or hydraulic respectively, depending on the ability of the cement to set in the presence of water. Basically classified are two parts, hydraulic cement and non-hydraulic cement. Hydraulic cement is made out of limestone, clay, and gypsum. Non-hydraulic cement is composed of lime, gypsum, plaster, and oxychloride. Hydraulic cement hardens when there is a chemical reaction between anhydrous cement powder with water. The hydrates that are formed are not soluble in water. It retains its strength and hardness below water. Non-hydraulic cement hardens when there is a reaction due to carbonation with the carbon dioxide, which is naturally present in the air. Hydraulic cement hardens underwater or when in contact with wet weather. Hence, it is suitable to work within any climatic condition. Non-hydraulic cement should be kept dry to attain strength. Hydraulic cement is used in multiple applications like concrete, mortar in monsoon swimming pools, marine construction, foundations, reservoirs, to name a few. Non-hydraulic cement is becoming redundant and obsolete due to the long duration of the time taken for setting of cement. Manufacture process of cement. First one crushing, second one grinding, third one preheating, fourth one blending, and the last one is packing and shipping. So let's start. First one, crushing. Crusher is a device that is designed to reduce large solid chunks of raw material into smaller chunks. Crusher will be erected near to the limestone quarry. The limestone and sandstone is transported from their respective quarry through the help of dump trunks to the crusher, which is directly passes the crushed raw material to the rootway so that the size is reduced to 25 millimeter. The crushed limestone is stored in the stockpile through stacker. Second one, grinding. The clinker and the required amount of gypsum are ground to a fine powder in horizontal mills similar to those used for grinding the raw materials. The materials may pass straight through the mill, or coarser material may be separated from the ground product and returned to the mill for further grinding. Third one, preheating. A preheating chamber consists of series of cyclones that utilize the hot gases produced from the kiln in order to reduce energy consumption and make the cement making process more environment friendly. The raw materials are passed through here and turned into oxides to be burned into the kiln. Fourth one, blending. A first approximation of the chemical composition required for a particular cement is obtained by selective quarrying and control of the raw material fed to the crushing and grinding plant. Final control is obtained by drying material from two or more batches containing raw mixes of slightly different composition. In the last one, I will discuss packing and shipping. Cement is conveyed from grinding mills to soils where it is packed in 20 to 40 kilogram bags. Most of the product is shipped in bulk quantities by trucks, trains, or ships, and only a small amount is packed for customers who need small quantities. Next, I will discuss cement production and decarbonization in front of you. I will explain to these branches technology to reduce CO2 from cement production. The capital cost will not be explored, rather we focus only on the potential challenges and ultimate limits of different technologies. First one, efficiency improvement. Efficiency improvement has been incremental in recent years as expected in a mature industry. The average thermal intensity across the globe fell from 3.75 for clinker in 2000 to 3.5 in 2014, around negative 0.5% a year. Given that both process and fuel-related emission account for a significant proportion of the total direct emission, both process modification and energy efficiency are important for CO2 mitigation. Energy efficiency can be improved through energy recovery, waste heat recovery, and increasing the proportion of dry and semi-dry process. Essentially, historically, plants would feed limestone to the kiln by producing a slurry using water, but the evaporation of this water is very energy intensive. Second one, waste heat recovery. Waste heat recovery assume that minor improvements continue, a low 5% improvement in fuel use. There are significant heat losses, about 35% to 40% from a cement manufacturing plant, mainly as a result of the airstream used to cool the clinker to 100 degree and the fuel gases. A significant fraction of the heat input to the system is lost by convection from the preheaters and kiln, clinker discharge, dust, and radiation. We have not considered electricity demand in our analysis. It is assumed that the sum total of electricity production where waste heat recovery can offset plant electricity demand, and this might require both a traditional steam waste heat recovery system and an organic Rankine cycle. Third one, lower crinkle and lower carbon cements. SEMs have emissions associated with their production, and the partitioning of these emissions between their production and final use is complex. Here we focus on direct emissions, given that construction managers have become more comfortable with these substitutions because of greater experience globally with them. The amount of clinker in a given volume of cement has decreased. Currently, the average global clinker ratio is around 0.7, but this is heavily influenced by Chinese clinkers, which are now starting to use fewer SCMS. We assume a base clinker content of 0.7, a reasonable reduction to 0.6 using current SCMS, but have investigated the effects of clinker down to a ratio of 0.5, which might be appropriate for so-called limestone calcined clay cements. These are a promising type of cement that is similar to currently commercial cements, and so might face lower barriers to commercialization than other novel cement formulations. Next, I will discuss alternative fuels. The use of alternative fuels can substantially reduce overall emissions compared with those of a fossil fuel plant, but ensuring the climate benefits requires careful analysis to traceably certify such reductions. According to the International Energy Agency, between 60% and 80% of the carbon in municipal solid waste is biogenic in nature. A biogenic function of 0.7 has been assumed here. The replacement of fossil fuels with waste-derived alternative fuels is a cost-saving way to reduce fossil fuel use in addition to being a relatively environmentally friendly method of waste management, particularly if care is taken to divert all recyclable material prior to use in the kiln. Next, I discuss biomass fuel. Biomass fuels are another option for reducing emission, assuming the biomass is CO2 neutral. Lafarge, as part of the Canadian Summit 2020 project, has run up to 10% substitution at its Path Summit plant in Ontario. The fuel used were hemp, sorghum, willow, switchgrass, and oat hulls in the first phase, with more challenging fuels such as demolition wood, treated telegraph poles, etc., are fuels to enable a hotter flame. In the second phase, reporter where positive and permits were applied for to increase substitution up to 30%. And last one, hydrogen fuel and or electrification. Hydrogen fuel and or electrification could potentially provide up to 100% of the heat in the system, but compared with the magnitude of reduction in CO2 emissions, the complexity and cost of designing and developing hydrogen-driven kilns are high. Importantly, no fuel avoids process emissions from calcination of CaCO3, 60% of the total. I will discuss digitalization in front of you. The benefits to cement plants from improved process control and next generation measurement devices are significant. Lafarge Holcim is a leader in this area and has started a plants tomorrow initiative which will roll out technologies including robotics, aluminium, and predictive maintenance. A plant certified under the scheme is stated to have a 50% to 20% operational efficiency. Again, more than 80% of Lafarge Holcim cement plants are already connected to its technical information system, allowing performance tracking and allocation of resources centrally. Next, I will discuss carbon capture and storage. Traditionally, emissions from both the kaolin and calcining limestone are combined into a single flue gas stream that passes through the preheating train and out of the plant. Because of the high CO2 concentration, 40% to 33% by volume. Basic thermodynamics indicate that it is in general easier to capture CO2 from a cement plant than an equivalently sized natural gas. 3% are qualified, 50% plant. Of course, the presence of dust, nitrogen oxide, sulfur oxide, and SO3. Post combustion. Post combustion capture involves removing CO2 from flue gases. It is either retrofitted into existing plants or built as an end-of-pipe capture technology for new plants. It is not necessary to go into detail as it to the different types of post-combustion capture, except to mention that there are multiple types, with some are more suited to cement production than others. Oxyfuel combustion. In oxyfuel combustion, capture of CO2 takes place after the fuel is burned with pure oxygen and recycled CO2 instead of air. It was the first technology heavily promoted for CCS on cement because removing the large proportion of nitrogen in the gas flowing through the plant theoretically lowers fuel consumption. There are no significant issues with cement produced under an oxyfuel atmosphere. However, it is difficult to retrofit the process to an existing cement plant. Direct separation sector reactor. The comprises a novel to method to calcine limestone, a large externally heated tube calcine ground limestone as it falls through it vertically. The re-engineering of the process allows the capture of the almost pure CO2 released from the limestone without substantially increase energy used, except a potential decrease due to less efficient indirect firing in the calciner or significant additional cost. Next, I will discuss emission from cement manufacturing process in front of you. The most significant environment, health, and safety issue of cement manufacturing is emission. Cement industry is potential anthropogenic source of air pollution. It has estimated that cement production originates about 5% of global man-made CO2 emission. The typical gases emissions to air from cement production include NOx, SOx, CO, CO2, H2S, VOC, dioxins, furans, and particulate matters. These major pollutants can be classified into two categories: gases and particulates. Fuel combustion process is a source of gaseous emissions, which include oxides of nitrogen, oxides of sulfur, oxides of carbon, and volatile organic compounds, and hydrogen sulfide. Quarrying, drilling, blasting, hauling, cement mill, fuel preparation, packaging, road cleaning, and stacks are source of particulate matter in the form of dust and carbon particle. Other source of emissions from cement manufacturing. There are many other sources of emissions from cement manufacturing, such as emissions from transportation, equipment used in the mining and transporting raw and finished material, fuel used for electricity production, for operating other process in cement manufacturing, types of fuel used in cement industry for few selected countries. SO2 and O2, but the highly alkaline condition in the kiln can absorb 90% of the sulfur oxides. Sulfur oxide emission can be controlled by using low sulfur fuel and raw materials. Health and environmental effect of cement plants emission. First, nitrogen oxide. Second, carbon monoxide. Third, sulfur dioxide. Fourth, particulate matters. And the last one is VOC dioxins. First one, I will discuss in front of you. Nitrogen oxides. Nitrogen oxides can cause or contribute to a variety of health problems and adverse environmental impacts, such as ground level, ozone, acid rain, global warming, water quality deterioration, and visual impairment. Affected populations include children, people with lungs diseases such as asthma, and exposure to these conditions can cause damage to lung tissue for people who work or exercise outside. Second one, sulfur dioxide. Sulfur dioxide in the high concentration can affect breathing and may aggravate existing respiratory and cardiovascular disease. Sensitive populations include asthmatics, individuals with bronchitis or emphysema, children, and the Algae SO2 is also a primary contributor to acid deposition or acid rain. Third one, carbon monoxide. Carbon monoxide can cause harmful health effect by reducing oxygen delivery to the body's organs and tissue, as well as adverse effect on the cardiovascular and central nervous systems. CO also contributes to the formation of smoke, which can cause respiratory problems. Fourth one, particulate matters. Particulate matters are emitted from quarrying, hailing, crushing, grinding of raw materials and clinker, fuel preparation, clinker grinding, and cement packing. Particulate matter is consisting of fine particles that can remain suspended in the air, which include dust, soot, and liquid droplets. The main environmental problems resulting from dust emissions is reduced visibility and deteriorated ambient air quality. When the dust is washed with rain, it can also pollute water bodies. Particulate emissions contain potentially harmful toxic metals and compounds such as lead, chromium, nickel, barium, which can pose serious health impact on human health. These emissions are toxic as it carries carcinogens, mutagens, hemotoxins, respiratory toxin, uh, uh, etc. Physical properties of such particles decides the degree of their effects on human health. And the last one is VOC, dioxins, heavy metals, and other pollutants. Cement-related emissions in trace quantity include VOC, dioxins, furans, methane, heavy metals, etc. The main source of VOC emissions from cement kiln is organic matter present in raw materials. Occurrence of VOC is also associated with incomplete combustion. Heavy metals emissions depend on content of these trace elements in fuel and raw materials, which is naturally present in low concentration in cement manufacturing. Dioxins are also formed in the combustion system when chlorine and organic compound are present. Choice of raw materials and fuel with low organic matter with low content of volatile and semi-volatile heavy metals can reduce these emissions. VOC are precursor to ozone formation, which can also contaminate soil and groundwater. It has been identified that VOC can cause retardation of plant growth, chlorosis, and necrosis in broad-leaf plants. Heavy metals and dioxins can also contaminate soil and water. Global warming and the role of cement industry. The cement industry is responsible for approximately 5% of global anthropogenic carbon dioxide emissions. Atmospheric concentrations of greenhouse gases cannot be stabilized without addressing this important emission source. The industry emits nearly 900 kg of CO2 for every 1000 kg of cement produced. As a result of the significant emissions per unit of cement produced, emerging climate change policies have the potential to place the industry at significant financial risk. Climate change, the role of cement industry. An industry-wide climate change response strategy and manage the associate environmental and financial risks then of the world's largest cement companies under the auspices of the World Business Councils for Sustainable Development sponsored a quantitative assessment of current and potential future CO2 emissions from the cement industry in regions of the world. Quantitatively, current and potential future cement industry greenhouse gas emission are evaluated under the new family of intergovernmental panel on climate change that we developed as part of the third assessment and documented in the special report on emissions scenarios. If the industry does not improve its current specific emissions, its relatively contribution to anthropogenic CO2 emissions would increase by more than one order of magnitude over the next century. The industry faces several challenges as it seeks to reduce its specific CO2 emissions, including its heavy dependence on fossil fuels, it depends on limestone-based clinker and the age and efficiency of its capital stock, especially in regions where future demand is expected to be high. So this was that conclusion of my presentation, and the last one is references. I hope you like my presentation. Thank you so much.